In this video, we will see how we can use embeddings to train regression and classification machine learning models. Actually, the process is exactly the same as how we use a tabular data, but I just want to quickly show you how we do it using embeddings. Okay, so standard libraries, and then here we are loading the compute embeddings module, and then for the regression we are importing this random forest regressor, the train test split, and some validation metrics. Okay, so we use this find food reviews data which we used in one of the previous videos. So basically it's the Amazon food reviews. Okay, so we have a summary, we have a text, and then we have the rating or score between 1 to 5. Then we also have the timestamp, the product ID, and user ID. Okay, so the three important columns are these three. All right, and then the summary and text both contain the useful information, and both are related to score, right? So in one of the previous videos, what we did is we took the summary and we also took the text and we combined them into a new column called combine, and then we use this combined column to create the embeddings. Okay, using this ADA version 2 model. So that's how we got the embeddings. So each embedding will has 1536 dimension, and then these embeddings we added them back to the data frame. So corresponding to each row we have the embeddings, and then we save that as a new data file, right? So that every time we need to work with this data set, we don't have to call this function, which obviously going to cost us, right? All right, so basically for every row here we have used summary and text to create embeddings, and we have added them back to the data frame. Okay, so let's load the data set with the embeddings. All right, and then when we read this file, the embeddings column, it's get read as an object or string, but we know this is a list of numbers, right? So here what we are doing is we are just converting the string to list of proper numbers, and then we want to split the data into train and test split. Our features are going to be these embedding vectors. Okay, in a normal regression case, we would have the tabular data features, right? The engineered features are some raw features from the tabular data, and our target variable is this score. Okay, and it is between 1 to 5. We are using 20% of the data for testing, the usual stuff. So we are using this random forest regressor. We are going to train 100 trees. We fit the data using the train, and then we are predicting on test data. Okay, so we already have the predictions. So we know y test and we have the corresponding prediction. So using these two columns, we can compute the validation metrics. So here we have mean squared error and mean absolute error. Okay, we use RMSE over MSE. That's because the units for RMSE will be the same as our target variable y, whereas this one is mean squared error, right? That's okay. We are going to look at only the mean absolute error. All right, for this model, we have got a mean absolute error of 0.5. So this means if the user rating is, let's say, 3, and on average we are off by 0.5. So which means we might be predicting between 2.5 to 3.5, whereas the user prediction is 3, right? So on an average we are off by 0.5. Or other way to look at it is, let's say if we have X number of records in the test data, half of that records we are able to predict accurately, but for the remaining half we are off by 1.0. Okay, so that's the other way to look at it. Now, whenever we train a machine learning model, we always compare how good it is performing against a base model, right? Now, this base model can be a dummy model where we simply take the average value, right? For example, here you ask, okay, how much this user likely to give the rating. All I do is I simply take the average rating of all the users, and whatever be the user, I simply say, hey, 3.5, for example, right? So for every user, we'll simply say for every user and every product, we'll just give the average rating, right? So here we take a y-test mean. Okay, y-test mean. So we are saying that's the prediction. That's how a dummy model would predict, right? So this one has a mean absolute error of 1.0, right? So what this means is if the actual answer is 2, this dummy model, it's predicting it as 3, between 1 to 3, right? It's 2 plus or minus 1. That's the mean absolute error. Okay, so our model is doing better. Now, again, we have only 1000 data points, and also we don't have enough samples to represent all 5 classes, right? So the goal is not to train a very accurate model and check how good it is performing. We just want to see the process, how we can use the embeddings to train a regression model. Okay, so with more data, we probably can reduce this MEA to probably 0.1 to 0.2, which is quite good. Okay, and that would be much better than a dummy model. All right, let's quickly look at classification. It's exactly the same. So we are using the same data, but this time instead of treating this target variable score, which is 1 to 5, we treat that as a label, class label, right? Anyway, we would have converted the class label, which is text, to some numeric. So we can use this y as it is in classification models. So here we have a random forest classifier instead of regression. And then for the validation, here we are using the classification report and accuracy scores. So the process is exactly the same. Here we would have the random forest classifier, everything the same. And first we are predicting, here we are making the predictions, and here we are computing the probabilities. Okay, in order to build a ROC curve, we need the probabilities. But for the classification report, we just need to supply what are the actuals and what are the predictions. So y-test is our actuals, and then the spreads contain our predictions. Okay, so here we have 5 classes. Now for these 5 classes, we can see the precision recall along with F1 score. Now it's not that great. I mean, the model, it's okay, it's mediocre, but we can still see the model is able to predict. So here we have a good precision, meaning when the model is making predicting something, it's predicting accurately, but it's missing because the recall is low, right? All right. So for this one, for the 5th, whenever the rating is 5, we have better both precision and recall. That's because we have a much many more samples, right? So remember, this data set has only 1000 records, and it's also very skewed data set because most of the records have user rating 5. All right, and then we can simply plot this AUC curve for the precision recall curves. So the yellow one, that represents the overall for the average for all the classes, and then the colored ones, these 4 and this one represent for different classes, right? So as you can see, for 5, we have much better area under the curve, which is 0.97. So we are able to predict or classify the rating whenever it is 5, right? And then we can see the green one, it is 3, right? So the lowest accuracy is for class 3. That's because, right? I mean, we can say 5 rating, it's a very good rating. 1 rating, it's a very poor rating. But 3, which is in the middle, it's hard to these users sit in the middle, right? So it's from the text, it's hard to say whether it is positive or negative. These are kind of neutral, right? So some are positive, some are neutral. So in that sense, predicting the class 3 is much more difficult compared to the rest of the classes. Okay. All right. What else? Yep. And 1 and 3, we have good scores. 1 and 4. The orange one is 2. 1 and 2. Yeah, so these are the lower ones, and the red is the fourth one. Okay, that's pretty much it. Again, as I mentioned, using embeddings to train machine learning models, the classifications and regressions, is not any different from using the tabular data features, right? But we just want to do it so that we'll have a feel. Okay, that's all. Thank you very much.